We are going to look in depth at starting with a center point and some known point on the circumference of a circle and finding the equation for that circle. And we're going to do this kind of from basic ideas. So the first thing that I want to look at is, what is the definition for a circle? A circle is a set of all points that are equidistant from a given point. That given point is the center of your circle, and so the circle itself is all of these points that are the same distance from this given point. And so a circle is just an infinite collection of points, essentially. The big idea is, what is the equation for a circle? How do we find that from this information? Well, one thing that we do know how to do is to find missing sides from a right triangle. And you look at this and you think, where is the triangle? We're talking about circles. We're going to impose a triangle on this. First of all, we can look at connecting this known point on the circumference to the center. And this is going to be a hypotenuse. And then we can look at the difference in this x direction and the difference in this y direction that meet at 90 degrees. And so there is the hidden triangle. So now we've taken this from something that we may not have known how to do, and we've brought this into the realm of something that we know how to approach. We know how to find missing sides for a right triangle. This is going to involve the Pythagorean Theorem. So let's review. What is the Pythagorean Theorem? Well, it is some base of a triangle squared plus some altitude of a triangle squared, and that's going to equal the hypotenuse squared. I purposely talked about this theorem in a slightly different way than is traditionally discussed. Typically we see a squared plus b squared equals c squared, and that is sometimes deceiving to students because we don't know exactly what the a, what the b, and what the c is, and it is incredibly important that the value that's traditionally called the c value is always the hypotenuse. It always has to be this side that is directly across from the 90-degree angle. That has to be your c value. So if we discuss the Pythagorean theorem like this, where we're talking about the difference in the base plus the difference in the altitude equal the hypotenuse, then we have a better understanding of where a squared and b squared come from. We don't necessarily have c squared nailed down, but we have a better grasp of what the a and the b is. And these are commuted here. It doesn't matter because this is addition. It could be a squared plus b squared or b squared plus a squared. It doesn't matter. But for my particular example, I want the base value first because that's the way I want to discuss this. So now looking at the base, what is this distance here? Well, we could use the distance formula in geometry. That would be cheating a little bit because the distance formula in geometry is derived from the Pythagorean theorem. But we also have a way that we can just, since this is a horizontal line, it is parallel to the x-axis, we are just simply moving left and right from a given position, so we can just take the difference of the two values. So we can take the initial x value and subtract the ending x value, and the difference of those numbers are going to be the linear distance here. And so we have a way without the distance formula of finding the range essentially of these numbers on this number line. And similarly, we can find this height in the same way. We can take one height and subtract it from the other, and the difference of those, the absolute value of those differences, is the length of the segment. Remember, in geometry, magnitudes of segments are always positive numbers because we are measuring distance. And so we're taking these differences, the absolute value of those, that's the magnitude, that's the length. So we can do this without the distance formula. The one that we would normally use the distance formula for would be the distance between this given center point and the point that we know on the circumference. But we can avoid directly calling this the distance formula if we are using the Pythagorean theorem. And again, the Pythagorean theorem is where we get the distance formula in the Euclidean plane geometry. All right, if we look at the larger number subtracted from the smaller number, we have 5 minus x minus y. The difference in the x direction is 5 minus x. Now remember, I mentioned that these are magnitudes. We're looking at the absolute value of this, so it could also be the same as x minus 5. And all right, I plugged in some values so that we can see the magnitude here. We have -4, which is our x value over here for this intersection point that gives us the 90-degree angle, and we're subtracting 5 over here. We get positive 9 because we have -4 minus 5, which is -9. The absolute value, that is positive 9. Now, the absolute value here is forcing everything to be positive. We're looking at distances, and so in geometry we had to have positive distances. If you look at the Pythagorean theorem, you see these terms are being squared. It kind of does the same job as the absolute values over here. It forces everything to be positive, so you get that nice feature. Looking over here at the y values, we need to know the difference between the two y values. So if we start up here, the y value up here is positive 4. And if you subtract the y value down here, we have -7. 4 minus -7 is going to give us a positive 11 there. So this distance vertically is 11. This distance horizontally is 9. And so you see in this calculation and this calculation, both we involve this center point in conjunction with values from this point. And we're trying to find the equation for this particular circle, but I also want to work towards the general solution, the general formula for the circle as well. And this is all involving distance formula as well. That's all kind of packed in here because it's all related back to the Pythagorean theorem, which deals with triangles, even though ultimately we're trying to answer a question about circles. So we have these values in here. And so we know our b value now, that's our base. We have a distance of 9. And we know our height, our altitude, which is this distance of 11. But we don't know this hypotenuse yet. But we're getting there. So the base value is 9. We're going to square that. The altitude is 11. We're going to square that. And that is going to equal our hypotenuse. But remember, our hypotenuse is also the radius for our circle, so we can rewrite this h as an r. And so we're going to have 81 plus 121 is equal to r squared. And so then we complete this arithmetic. So the radius squared is 202. Now I don't actually have to take the square root of this because when we look at the formula for a circle, it tends to be that it's equal to r squared because we have h squared here and r squared is replacing h squared. So I don't have to take the square root of this right now. But if you were looking at the distance formula, you would take the square root of this to know the distance of the radius itself. Remember, this is the radius squared. So I haven't found the radius specifically yet, but I'm one step away. I merely need to take a square root. Now, putting this all together, think about what we've done here in finding this radius squared. And this is going to bring us to the distance formula as well as build into a general formula or a general equation for circles. This 9, we found this essentially, we took this value here and we subtracted it from some value over here. So this was a difference of x terms. And where specifically was that x term? Well, we took this value and this value here. So if this is some value h, and this is some value x, we have a couple of versions that we could do with this because we have the absolute value here. So this is h minus x, or we could have x minus h are the two options. And again, absolute value of these things gives you back the same value. We're good with this. Due to the convention that we typically use, we use the form of the x minus h. So this 9 is really x minus h squared. And then the 11 came over here from this. Let's call this term k. So this center is the point hk. And then over here, this is y. So this point on the circumference is xy. So we had y minus k was over here. We had the absolute value of y minus k. And then we squared that. So we're adding y minus k, and we're squaring that, and that is equal to the radius squared. So this right here is the general form of the equation for a circle. So now we're going to use all this information to get specifically the circle that we have here and answer the question that's being asked here. And then we're going to take it one step further and show you the direct relation to the distance formula. So if I wanted to know the hypotenuse directly, I simply used that distance formula. So let's answer specifically the question, what is the equation for the circle? Well, I took x minus h, which was x minus 5. And I squared that, and I added to that y minus k, which is negative 7. So that forces a positive 7 there since it's double negative. That is squared. And then this is going to be equal to r squared, which is 202. And so this is specifically the equation for the circle that we had the given center and we had a point on the circumference. So this is specifically the answer to the question we were asked here. So I've generalized this, I've given a specific answer, and then one more substitution essentially gives us the distance formula. So that's super important, so I want to look at that. I'm going to do a slight relabeling of our points. Instead of calling this h and k, we are now going to call it x sub 1 and y sub 1. Over here on the circumference, we're going to call this x sub 2, y sub 2. We are used to this notation since Algebra 1. And so now I want to look at this general form for the circle. And this is a reflection of the Pythagorean Theorem again. So what is the radius here? What is the distance between this point and this point? So now we're looking at the distance formula. So radius is the same as distance. And so I'm looking at the point x, or this x value here was this x over here. So this is x sub 2 minus x sub 1, the former h value, squared, plus y sub 2 minus y sub 1 squared. Again, we are used to that kind of notation from Algebra 1. This is all going to be equal to the distance between these 2 points squared. So we substituted from hypotenuse to radius. Now we're substituting from radius to d for distance. And now if we take the square root of both sides, we know that d specifically equals the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. That is our Euclidean distance formula. Hopefully this helps make sense about how all these things tie together and gives you a better understanding of where exactly the equation for the circle comes from. Keep in mind that this equation for a circle is not a function. If you look at this and try to do a vertical line test, you'll touch the top and the bottom of the circle. So this is not a function, and this formula will not be a function. This equation for a circle is not a function. Cheerful Calculations.